Doesn't mean that we're necessarily experts at it. Doesn't mean that we can necessarily solve any derivative with mental math. But we have all of the rules in our cards for any derivative that we could possibly need to find. Might be hard, but wouldn't be possible. So you guys, at the end of last chapter, started applying derivatives to related rates, finding how fast something is changing with respect to or in a certain scenario where possibly multiple variables are involved. That's one type of application. But in sections 3.1 to I think it's 3.4, if you guys want to put a chapter title, this is going to technically be called Chapter 3A. We're splitting Chapter 3 into 2 parts. Our hope is by the end of the semester to be all the way through the end of Chapter 3, so 2 more tests. Chapter 3A and Chapter 3B. Chapter 3A, the whole chapter is applications of derivatives, more applications beyond related rates. But you might be like, oh no, they're all word. No, they're not all word problems. Praise the Lord. 3.1 to 3.4, 3.3, 3.4 is all about graph analysis, or maybe a better way of putting that is behavior of functions or function behavior. So if you want to title it in your notes. Chapter 3A is function behavior or behavior of functions. So the first test we're going to have is all about behavior of functions. Derivatives help us describe what's going on in a given original function. And some of you might be wondering, but you probably have been too scared to ask, what happened to this guy? Anybody been curious about that? As I was starting to explain it to you that day on the overhead, I realized I was like, man, this vocab you're not ready to see yet. It'd be nice if I could show you the vocab first, like critical numbers and relative local extrema and absolute extrema. I was like, man, it'd be nice to show them the vocab before sending them on the assignment. I technically have 2 assignments. One of them is just a function with the first derivative, the second one function with the first and second derivative. We're going to get some of the vocab down in this first section or 2, and then we're going to go ahead and go back to that AP number 1. So that card matching using partners, etc., it is coming. It is going to be a thing. So you might want to reconnect with the people that you thought you were going to group up in. If you were going to pair up with someone else, you and someone else were going to do an assignment. It's coming. It's coming right about now because, as you guys can tell on this page, extrema on an interval and absolute extrema, some of the vocabulary that were on those descriptions that we were reading. So I tabled it just because I was like, no, let me just get you guys through all the derivative rules, then we'll come back to that card matching assignment. So Chapter 3A, all about analysis of or behavior of functions, how they move, how they change, and how the derivatives help us with that. And let me just give you a peek at where we're going. After section 3. I think it's 4. After section 3.4, when you have a test, where I want you to be is able to be given any function for our level. I shouldn't say any function in the whole wide world because there's some really nasty ones, but any function on our level and find its graph with a full, complete analysis of its behavior without a calculator. Remember last year? We found test points between things like zeros and horizontal vertical asymptotes. And we were kind of guessing at graphs of polynomials and rational functions. And we did trig and stuff too. But I was like, without calculus, we can't do this precisely, so we're going to kind of guess and get it to be good enough. With all of our calculus that you now know with derivatives, we can go a lot better than good enough. So let's go ahead and start on that journey. And that journey is going to take us 4 different sections to be able to think about all the different ways that functions move and change and all their different behaviors, etc. And then we'll get to the point where by doing or going through a list of 15, technically 14 and then a sketch, putting it all together, 15 things you should be able to, without a calculator, show me a graph of any function for our level with a full analysis of its behavior, when it's increasing, when it's decreasing, when it's concave up, when it's concave down, where it has relative minimums and maximums. I should say minima, that's a plural. Maxima, absolute, extrema, if they exist. What am I missing? And points of inflection. And that's all to do with graphs, which might be like, okay, whatever, yay, we're learning how to graph stuff. But guys, all of these things as far as minima and maxima and points of inflection, increasing, decreasing, have applications to all of the different movement, change, behavior of functions in real life too. And the most basic one you guys know is motion with physics as being one. Each of these physics apply in a certain sense. When it's stopped, when it's rising, when it's falling, etc., etc., etc. So here we go. 3.1, part 1. We'll finish it on Monday. Absolute. What's the word absolute mean? It's an English word, absolute. I mean, a lot of our words are. But in English, what does absolute mean? Kind of, yeah, total, like the absolute best, the total best, right? Is absolute used in science anywhere?
Yes.
Where?
Absolute zero.
Absolute zero, yeah, that's what I was thinking too. Absolute. So if you look up here and see absolute extreme values, extreme, you guys know the word extreme too, right? Extreme. And when we're looking at a graph, extrema, what they're talking about, an extrema is an extreme value. It's a shortened way of saying extreme value. An extreme value, you can think about minimums. Absolute is an absolute max value. Now, I do want to fill in something right now as far as extrema. If we're ever talking about value of my honors pre-cal kids from last year, you had more exposure than my regular pre-cal kids. The extreme value of and then at. At. Do you guys remember where the x goes and where the y goes? Where the function value goes and where the independent variable goes? How do we fill in this if it says the extreme value of and at? Who goes where? The y function is going to go, and then the x value is going to go there. And t, that's why the when. But since I went ahead and put x, I'll leave it there. Whenever it's talking about the value itself, if you look at these graphs, and let me zoom on the graphs themselves. The first graph that you see, what is the maximum value? The first graph that you see, what's the maximum value? Of? What's the maximum value? Nope. But you're close. Maximum value, we're saying what's the highest value? What's the highest? Oh, what's the highest it goes? The English totally tells you this. What's the maximum value? What's the highest it goes? Well, it goes to 5, doesn't it? The maximum value is 5, but at or when or for 2. Does that make sense? So the value is 5. The highest it goes is 5. Maximum, highest, 5. 5 is the highest it goes. When does it happen? For what x does it happen? Where does it happen when x equals 2? So what would be the min value? At. Does that make sense, the terminology? Has a max, has a min, has a highest, has a lowest. The highest is, the value is 5, the lowest is 1. When does it occur? Highest at 2, lowest at 0. Now what's going on over here in letter B? What's the maximum value? Ooh. Why is there none? There's a hole. And pause. Might not actually be a hole. There might not actually be a hole. It might be instead, check the interval. What does a parenthesis mean? Yeah, the original function is continuous, aka the original function has no holes, but when an interval says -1 to 2, not -1, not 2, we're not allowed to consider the end. So in the original function, they're going to be fine. We're not going to see any holes in the original function. We're not going to see any domain problems, but the interval says you're not allowed to use him or him. Okay, fine, well then there's no max. I mean, it's bounded by 5, but it never hits 5, so I can't say value of 5 on the interval. It doesn't hit there. But what can I still say? Yeah, minimum value of same, right? 0. Why? It happens in between. What's so special about minimum occurring? Thinking about calculus and derivatives. Derivatives, slopes of tangent lines. What's so special about that point? Derivatives and slopes of tangent lines. What's so special about the point 0, 1? It's a what? Yeah! It's a horizontal tangent line. AKA, what's going on right there? F prime of 0. Huh. Wonder if that's a clue. Moving on, letter C. We still have a closed interval from -1 to 2, but all of a sudden G is not continuous. So we are allowed to consider endpoints, but oh, that would be mean. AP guys give us a function, and guess what? If we plug in 0 and plug in 0, they don't match up. Why? Because at a point, there's a discontinuity. Stink-a-dink. So if we were to take his derivative, 2x can be 0, can have a horizontal tangent line at 0, but 0 is not allowed. Is there a horizontal tangent line? No. Why? It's not continuous, and if it's not continuous, it's not differentiable. But long story short, looking at the graph, is there a max of 5 at 2? But what did this quick little redefining of G, of F, I should say, into G, what it took away min. So there's no min value. What caused problems in these 3 examples? What caused problems to allow there to not be a min or not be a max on a cutoff graph? Either an open interval or a discontinuity. What made it so that there would not be a min or a max, or there might not be a min or a max? An open interval, discontinuity. Okay, moving on. That was just all intro. Let's talk about local or relative. Absolute, very highest, very lowest, local or relative. You can see either one. I think in the cards on the overhead that I was showing the other day, I don't know, that was a couple weeks ago, I think it was using local. But relative isn't a way of saying it. Absolute, absolutely. Absolute is absolutely. Absolute is totally, completely, over the entire interval that you're looking at. Local or relative just says it has to be true for the region right around it, right? Local versus, you can think local versus national. Local is very different than national. Any of my guys that are in sport, being the best in the nation is very different, right? If you have a favorite restaurant, like, yeah. Would you say it's the best national spot? Be true for the region right around it. Just has to be true for the region right around it. Absolute has to be true absolutely for the entire thing of whatever is given to you. So relative or local extrema occur at the highest or lowest values contained within an open interval. And you could say contained within, if it helps, a smaller region, and the point is around. The smaller region around. Something has to be the highest or the lowest coming from two directions, not just one. The highest or lowest coming from two directions, not just one. Does not need to be the highest or the lowest of the entire function or the entire domain that's been studied. It just needs to be a high or a low, a highest or a lowest. So a difference between absolute and local relative. Absolute, it's the highest, the lowest of whatever's been given to you. Sometimes with some sort of restricted interval or domain that you're looking at. Local or relative just has to be a highest or a lowest. So each of these that are graphed below, each of these are relative. They could be absolute as well, to be honest. They could be absolute also, but they're at least relative. I can see a little region around it. I can see a little region around it, and I can see a little region around it. So for each of these, just do a quick sketch of the graph. You don't need to label what the functions are. You don't even need to label the specific points per se. But quick sketches of the graph. Each of these are relative. And actually, to look at all of them, as they keep going, if they were to keep going in the same way for forever, this would actually be an absolute highest also. It's relative to the region around it, and for the entire function, it's absolutely the highest. This one, it's relative to the region right around it, and it's absolutely the very lowest. And, okay, well, this one's a little weird. Doesn't sine just oscillate like a wave? So a sine oscillates. Is this the highest it goes? Yeah. But how many times will sine hit its highest? Over and over and over and over. So is this the only spot of the highest? No. But pi over 2 is one example of where sine hits the highest of 1. And 3 pi over 2 is one example of where sine hits the lowest at -1. But the max value is 1. The min value is -1, but they're going to be at a lot of different locations. But these are actually also relative and absolute. We'll look at examples soon or where they're relative that aren't absolute. But that's not the question being asked. The question being asked is the derivative value at each of them. Why? Because I told you the point of chapter 3a is, can we use our calculus to do or to analyze, to figure out the behavior of functions? Ow, that hurt. Coming back. What's the derivative at the first one? We can call this guy f. So for f of x, what's the derivative value at 3? Derivative is slope. Slope of the tangent line. What's the derivative without even solving? What's the derivative looking at the graph at 3, at the relative max, at the absolute max? Yeah. So f prime of 3 equals 0. Okay, what's the derivative value of the second one? At the min. It's a min and the min. We'll call this guy g. What's g prime of 0? Good guess, but no. Look at this guy. This guy, we can call him h. What's h prime of both relative max? What's h prime of pi over 2? We'll come back to it. The primes of these two? Now do your guess. Now be confident. 0. What's the difference between these and that? Why are these 0 and that one not? Yeah, a couple of different ways of thinking about it. Sharp point is the easiest. What always happens at a sharp point? Come on, back to the forever cards. Yeah. And what's the slope before the sharp point? I don't know, something negative. What's the slope after the sharp point? Something positive. Does it hit 0 in between? These ones it does by IVT. Positive slopes, negative slopes, has to hit 0. Positive slopes, negative slopes, has to hit 0. Negative slopes, positive slopes, has to hit 0. Why? Because they're smooth turns. But sharp turns, negative slope, positive slope. Did it ever hit 0? No. Why? This is an example of a piecewise function that sometimes is a negative one, sometimes is a positive one. Oh yeah, absolute value is a piecewise. And what happens when they clash in the middle, because every derivative is defined by a, what's the derivative definition of the derivative? Come on, we just looked at it on chapter 2 corrections. Definition of a derivative, the limit. Oh, as h goes to 0. A limit? What has to be true with a limit? You guys have to agree. Are the slopes agreeing from either side? This one is getting closer and closer and closer to 0, closer and closer and closer to 0. They're agreeing. They're approaching the same smooth, nice turn horizontal tangent line. Getting closer and closer to 0. They're agreeing, but this one, I'm going this way and this way only. I'm going that way and that way only. Ooh, our political climate in America. Anyway, what's going on as they come together? No one's willing to go or to give or to compromise. Ooh, this is getting good. What's going to happen? Clash. So what's the derivative at any sharp point? It's a forever card. DNE. Destroyed. DNE for destroyed. Got it. Interesting, yeah? Interesting, yeah? So question. If you claim Christ, are you supposed to be a sharp point? No. Maybe you're not supposed to be a linear function. Maybe that's better. You're supposed to be a curve. But coming back. Sharp point will not exist, so the derivative does not exist. But guys, check it out. Isn't this also a relative min? If I didn't show you this example, you could be like, hey, relative mins and maxes are every time the derivative is 0. Yay! Well, that derivative is not 0. That's a relative min. Okay. Relative extrema every time I have zeros or DNEs. You're getting closer. But can I show you one more example real quick? Because we're trying to figure out when do relative and even, hence absolute, extremas occur. Question. What about this guy? Is there a place where this, what I use, F and G and H and I? J. Okay. Does J, which is looking like a cubic function or a tangent function, either one, does J have a horizontal tangent? He flatten off anywhere? Doesn't he? J prime of 0. Oh, he must be a min or max. Is he a min or a max? But he has a derivative that equals 0. I know. So what's the struggle? You guys ready? When do relative? We'll get back to absolute in a second because he's kind of tricky. There are things called endpoints that we have to be careful of because when you cut a graph, there can be a highest. Well, there can be a highest where the domain would not allow a highest. If you cut it, well, that could be a high, whereas parabolas normally have no max. Anyway, coming back. So let's not talk about absolute. Let's talk about relative or local. Thank you, ma'am. Make sure they're both here. Yeah. When do they occur? Where do they occur? How can we use calculus to find them? Well, I think we should find the zeros and the DNEs of a derivative. I think we should find the zeros and the DNEs of a derivative. But it's not enough just to find them. There must be a way of testing them to see whether or not they're a max or a min. But our candidates for relative / local extrema are going to be at the zeros or the DNEs of the derivative. Only at smooth turns and sharp points can there be a relative min or a relative max that's the highest for the region around it or the lowest for a region around it, which might be the lowest, the highest also might not be. We'll have to save that for another day. But not every time you have a 0 or a DNE will it be a min or max, so we have to have a way of testing. Here we go. Is there a special name for that whole zeros or DNE thing? Why, yes, indeed there is. We call them. Hey, it's some other vocab from those cards that we looked at. Critical number. Let a function f or g or h or j, whoever, let a function exist. Ooh. Has to exist first at a point. If it doesn't exist, like the one that we saw with the hole, if it doesn't exist, we're in trouble. But first of all, let a function f exist at a point at x equals c. If f prime of c equals 0, 0 is the derivative, aka horizontal tangent lines, or f prime of c does not exist, undefined points of a derivative. If you want, you can put HTL for that guy, and you can put sharp points or VTLs? Do you want that reminder from earlier on in the year? Then C is a critical number. We're just defining something. Critical numbers. Critical numbers are candidates. Candidates for what? Candidates for relative extrema. Candidates, meaning they're elected? No, meaning they're the possible. The ones that are, wording is not helping me today. The English language is not working for me. You probably think I'm just going off this whole political or whatever because of the elections. No, they're actually called candidates, like the AP guys called them the candidates for relative or absolute extrema. So critical numbers are the candidates for relative or local extrema. Also called critical values, critical points. I'm going to have you guys put up here in parentheses the candidates for local, relative. Sorry, I finished that word. I just ran out of room. Critical numbers, candidates for local slash. Let a function f exist. If the derivative is 0 or dne, then c is a critical number of f, aka critical values, critical points. And here's the cool thing. If it is really just a fraction. Now, I'm not saying quotient rule. I'm saying if you're done, you found the derivative, it can be written as a single fraction. The shortcut, which we actually saw last year when we were doing solving inequalities for rational functions, we were trying to find key numbers to put on a number line. Those key numbers were the ones where we tested the intervals and sign charts to see true or false. Ooh, this is all going to come back together. We use way, if you can make it a fraction, if you can make the derivative a fraction, the 0 from the top. And the DNEs will come from the bottom. It just saves a little bit of work, a little bit of mental gymnastics. DNE will only occur of a derivative when the bottom is equal to 0. Ooh, or unless it's a piecewise function that doesn't meet up. But that's going to be a different case. But if you can write the derivative as a single fraction, the zeros come from the top, the DNEs come from the bottom. So when we're doing critical numbers, literally, guys, this is what you do. You find the derivative, see if you can write it as a fraction, find the zeros at the top, the zeros at the bottom, and say boom, 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 boom. Critical numbers. Pause. Ugh. Almost. Finding numbers, you actually check first the domain. You check first the domain. P.S. I'm underlining this because it's important, because it's something that kids normally leave off the quiz, and I have to take off points. You have to check the domain first. You have to check the domain first. Then take your derivative. Try to see if it can be written as a fraction. Find the zeros at the top and the zeros at the bottom and say, ha-ha, as long as it's in the domain, these are my critical numbers. If it's not in the domain, well, forget him. He's illegal. Cross him out and ignore. Find the domain and find the derivative. See if you can write it as the DNE. Let's done. Critical numbers. Why am I making a big deal about this? The forever card. Forever number, help me out. 18. First of all, it's a forever card. Second of all, it's vocab that we're going to be using for the rest of the year talking about critical numbers. It's vocab that we're going to be using for the rest of the year talking about critical numbers. Why? Because they're the candidates for local extrema. And in real life applications, it's kind of important sometimes to be able to minimize or maximize different quantities. Honors pre-cal kids, you might be thinking back to this whole parabola worksheet thing where we had like a fence around a field trying to find the minimum or maximum area that can be enclosed. It was kind of a hidden calculus problem, but of a very easy parabolic or quadratic function that you could actually find the min or max of. In real life, not everything is a parabola. In real life, not everything is a parabola, hence why we need calculus, because functions that are not parabolas, how do you minimize or maximize? Well, with a derivative and critical numbers, of course. And honors pre-cal kids wondering I'm talking about this guy from last year. But don't worry. Derivatives make this way easier than having to complete the square and find the vertex of it. Ugh. Non-honors kids, if you want to take a peek at it, it's right there, but it's okay, you'll be fine. I'm going to label this guy. I'm going to label each and every point. So we're going to name this guy to be A. We're going to name this guy, the X value, to be B. This guy to be C. This guy to be D. If you ever see dotted lines on graphs, what they're just trying to show you is exactly where it hits on the graph. Exactly where it hits on the graph. I'm not going to label all the Y values, so I'm not going to ask you for all the values of. I'm just asking for the at. Identifying what is going on at. So at X equals A, and then B, and then C, and then D, and then E. Oh, and we're done. How would you guys best label A? Absolute minimum or maximum? Min? Relative or absolute? Mm-hmm. Technically, we could say both, but yeah. Oh, sorry, I was putting in the first one I saw. I forgot that was up there. Thanks, Thomas. Okay, keep going. Fill in relative or absolute, REL or ABS, rel or abs. And if you're not taking notes, you should at least be paying attention. So label, relative or absolute, min or max. A couple more seconds. Relative or absolute, min or max. Letter B, relative or absolute? Min or max? Good. Letter C, relative or absolute? Min or max? Letter E, sorry, D. And letter E? You guys can pack up. Derivative 0, derivatives D and E. Endpoint. On Monday, we'll figure out what's going on, but hold on, pause. It might be a great idea this weekend, either CalcAB or Patrick JMT, to go check out function analysis, behavior of functions with relative extrema. And just watch an example or two. I'll go ahead and post a link in Google Classroom because then you're like, psh, I have an idea of what's going on for Monday. Bye, guys. See you later. The assignment might be to watch and then just turn in that you watched.